Well, Professor Clements with you as we continue our study of electricity and now magnetism. And we're investigating in this chapter some natural, you might say, magnetism, permanent magnets, and then electromagnets. And especially interested in the force that magnets can apply to charged particles. An example of effect of magnetic force here, you can see the aurora. And this occurs because the Earth's magnetic field guides particles, mainly from the sun, into our atmosphere near the north and south magnetic poles. And those particles energize molecules in our atmosphere to then glow. So we get the nice aurora. We'll talk more about that when we talk about the Earth's magnetic field. But we have various types of magnets, horseshoe magnets, bar magnets, and they will attract magnetic material, and we'll get into that force just a little bit. As you see the labels here, we see that magnets are labeled with North Pole and South Pole, North-seeking pole and South-seeking pole. In a sense, there are two poles, somewhat similar to having two charges, positive and negative charges, but there's a major difference. There are no single poles. No single South Pole, no single North Pole has ever been found. There are single positive charges and single negative charges. So some similarities, some differences, and we'll continue that kind of contrast as we talk about magnetism and relate it back to electricity. The Earth does have a magnetic field. It's basically as if there was a bar magnet through the center of the Earth, with the South Pole of that bar magnet near the North Geographic Pole. And consequently, if we take a compass or a bar magnet that has North Pole labeled, that's the North-seeking pole, comes up to here. And that's the way it's been throughout your lifetime, with the South magnetic pole at the North Pole of the Earth. We'll get into some discussion on changes that can occur. The major thing you should block from your mind is this picture of a bar magnet through the Earth. There is no solid bar magnet at the center of the Earth. There's a different mechanism that creates the Earth's magnetic field than a permanent magnet. Some force that we can observe, and you possibly have observed, between magnetic poles. The opposite poles attract. North attracts south, south attracts north. But like poles repel. The North Pole of one magnet will repel the North Pole of another magnet. So magnets have poles, they attract and repel. Here's the difference between isolated positive and negative charges and poles. If you would take a bar magnet and cut it in half, you would not have a South Pole on the left piece and North Pole on the right piece. Instead, you would observe that now this smaller chunk of magnet again has two poles, a south and a north. Now if you further divide this, you'd have a south and a north. If you'd further divide this side, you'd have a south and a north. And so on and so on. You cannot isolate a single South Pole or a single North Pole. We can lose permanent magnetism if we magnetize something, apply some external magnetic field to a ferromagnetic material like iron, then there will be permanent magnetism created in that. Permanent is in quotes. If you heat up a magnet, raise its temperature past the Curie temperature, the permanent magnetism will be destroyed. And we'll talk a little bit in the future as to why that occurs. And we can remagnetize if we take away the temperature source and the magnet cools. It will cool off with the, again, south-seeking pole against north-seeking pole. And if we take the blowtorch back here and heat this up again, raise its temperature too high, we would destroy the permanent magnetism that was built into that piece. Inside a permanent magnet, there are domains that in the permanent magnet line up. These domains, having a magnetic field in a certain direction, when a material is unmagnetized, these small domains, many small domains, have more or less random magnetic field, net magnetic field, and they add up to zero. As the material becomes magnetized, those domains, the magnetic field inside those domains becomes aligned and adds up as a vector to produce a measurable amount of permanent magnetism in the material. We can have magnetic fields created by electrical current, and the MRI machine actually uses a high value of electrical current, and in order to not heat up the material here, I²R type heating, the conductors are superconductors with resistance of 0. That's an interesting application of this effect known as superconductivity. But going back a little bit, this ferromagnetic material, we have domains in that ferromagnetic material, and we get some alignment of those domains. The domains themselves are created by the alignment of quote-unquote spin of electrons. Electrons are charged objects. They have a negative charge. It's incorrect to think of them something like a basketball that is spinning, and therefore that charge in motion creates a magnetic field. They have a characteristic like spin, but not quite like it. They carry with them a small magnetic field. The electron has a small magnetic field. There are trillions upon trillions of electrons in materials. If we can get the electron spins to line up, then we can get a measurable magnetic field. So there's our ferromagnetic material, and our magnetic domains are just regions where those spins are lined up. And again, we could go back to this picture on the left. If we would take a hammer to this and cause a lot of vibration, we can jostle those spinning electrons, and they would no longer be aligned, and we would lose our magnetic field. Or we can increase the temperature. That gives random motion, collisions between atoms, and the spins would be unaligned. Here's an example of magnetic field created by current versus a permanent magnet. The iron filings here, you can see, have a similarity of arcing from one end to the other, making an arc. These are the magnetic field lines, showing the location of magnetic field lines. As the magnetic field causes a force on the iron filings, and they can tend to line up along the magnetic field lines. If we pass an electric current through a coil of wire, a solenoid, then we'll find there's a strong magnetic field inside the wire, and there's this somewhat dipole pattern of magnetic field outside the wire of the arc of the iron filings that are laid out for you there. An electromagnet, if we pass the current in a coil around ferromagnetic material, the magnetic field created by the current in the wire will encourage the electrons in the ferromagnetic material to line up and give us a stronger, more concentrated magnetic field. So we have junkyards that lift cars with electromagnets. We have doorbells that have a property of magnetism, and some other attached equipment, but a little bit similar. We have a current create a magnetic field that can create a force. In our technology today, with currently our hard disk drives are magnetic effect, where there is a write head and a read head in the hard drive. As the platter of the hard drive spins around, there's this read-write head, and it can magnetize a small area on the disk, on the hard disk, when we're writing. If we're reading, then we can sense the direction of that magnetic field that's been laid down. One direction of magnetic field would be a 1, the reverse direction would be a 0. Ones and zeros then form the data recorded on the hard disk. And of course, this is a much magnified illustration. We can get a couple of terabytes, 2 times 10 to the 12th bytes recorded on a platter here. So you realize these are very small areas that are being magnetized and then sensed. Here's a picture of perhaps an atom. This is the simplified view of an atom where the electron's in orbit, and that circulating charge would create a magnetic field. But it's more important, it's the spin, this quote-unquote similarity to spin, that lets the electron produce a magnetic field. We can map out magnetic field around a bar magnet using a compass, and you can see here what would happen if you place many little compass devices around a bar magnet. They would follow this kind of loop, this line around. The loop does not start or stop at the north and south poles. For the electric field, they started at the lines start at positive charges and ended at negative charges. But for the magnetic field, it's a closed loop. It's a complete loop. There are no magnetic charges, though the lines do not start or stop at a certain place. The magnetic field lines are loops. Here's a picture showing how magnetic field is created by a current. So here's a wire that's carrying current towards the top of the slide, and there'll be a circle with a constant value of magnetic field on that circle. Closer to the wire, the magnetic field will be stronger. Further from the wire, the magnetic field will be weaker. Again, I is our symbol for current. We'll use B for the strength of the magnetic field. And we'll encounter a couple of what are called right-hand rules. If we put our thumb in the direction of the current, our fingers can wrap around the wire and our fingers point in the direction of the magnetic field. Drawing these three-dimensional situations on paper requires a little notation. So on the loop here, where the magnetic field is coming out of the paper, we put a circle with a dot in it. That tells us the vector, magnetic vector, is coming out of the paper. And we put a circle with an X in it to show us magnetic field is going into the paper. So you'll see that notation often as we go through this chapter. We'll denote magnetic field coming out of the paper by using a circle with a dot, magnetic field going in with a circle with a cross. This would be the tail feathers of the arrow. This would be the tip of the arrow that shows that direction. Now, right-hand rule for moving charge particle. If our charge is moving in some direction here, we'll do a combination going through this equation. This equation will give us a calculation of the magnitude of the force, and we'll use our right hand to get the direction of the force. And this drawing is actually wrong, and we'll explain what needs to be done here. But we have some charge. We have a velocity for that charge, so this is not voltage, this is velocity in meters per second. The magnetic field strength will be measured in Teslas, is our standard unit. And then we have some angle in between the velocity vector and the magnetic field vector. So QVB sine theta. The way to properly use the right-hand rule is to put your fingers in the direction of the velocity and then have your wrist oriented such that you can easily bend your fingers into the direction of the magnetic field, and then your thumb will show the direction of the force. So that's the way that we're going to do the right-hand rule. Our fingers can be in the direction of the velocity. We'll rotate our wrist so we can easily bend our fingers into the direction of the magnetic field, and then our thumb will show the direction of force. So we'll go over that in class with you. So here's a particle, a positive particle traveling to the west, and you can practice with this. If you would extend your fingers off to the left here, use your right hand, point your fingers off to the left. Now rotate your wrist and to a place where you can bend your fingers back into the computer screen, and you'll have a thumb that's going down. The force would be down. So we're going to take our fingers going into the velocity direction, bend our fingers to point into the direction of B, which is into the computer screen. Your thumb is pointing down. So that's the direction of the force. That's our right-hand rule that we will use. So here is a situation where you have a uniform magnetic field, the circles with the crosses. Is the magnetic field going into the paper or out of the paper? It's going into the paper because you see an X. The magnetic field's going in. Let's take the charged particle up here. Notice it's minus q. It's a negative particle. Perhaps it's an electron. So we would take our fingers, put them in the direction of the velocity. Rotate your wrist so you can easily bend your fingers into the direction of the magnetic field, into the computer screen here. Your right-hand rule would tell you the force would be up towards the top of the screen. Well, there's a modification of the right-hand rule. If the charge is negative, you have to reverse the direction your thumb points by 180 degrees. So fingers off to the right in the direction of the velocity for this situation at the top of the circle. Off to the right. You're rotating your wrist so you can easily bend your fingers in the direction of the magnetic field into the screen. Your thumb points upward. Because it's a negative particle, you must reverse the direction of the force and cause it to go inward. So take a look here. From first semester, we have velocity and force perpendicular. We've seen this arrangement before in the first semester. What did we call this type of motion? When the velocity and the force are perpendicular to each other and they stay perpendicular, you can use right-hand rule all the way around here, and you'll always find that the force is perpendicular to the velocity. What did we call that type of motion? We called it circular motion. In fact, uniform circular motion. If the magnetic field is constant, the velocity will stay constant. This force does no work on the moving charge. The force is perpendicular to the direction the charge is moving, so there's no change in kinetic energy. Work causes change in kinetic energy. There's no work because the force is perpendicular to the motion. We have circular motion, uniform circular motion, and this force is a centripetal force. This force is a centripetal force. And we will work with centripetal force again, mv squared over r, where v is the velocity, mv squared over r is the centripetal force, and we'll use qvb for the magnetic force. Why don't we have to worry about the factor of sine of theta? The general formula for magnetic force is qvb sine theta. Why am I dropping the sine theta factor? It's because the velocity and the magnetic field here in this picture are perpendicular to each other. So the theta is 90 degrees and sine of theta is a 1. So our relationship here will be qvb, that's our magnetic force, equals mv squared over r. Television screen, old type television that has an electron gun in the back, not a flat screen TV, but an older type TV or older type computer monitor. You should not really do this. We'll explain why, but if you take a permanent magnet near the front of that screen, that magnetic field will go through the glass and it will cause a force on the electrons and deflect the electron beam one way or another. The reason you don't want to do this is there's also a film of metal behind here, and you can magnetize that metal and permanently distort your picture. There are ways of removing the magnetism from this metal, but most people don't have the equipment to do that. Another example here of magnetic force, where the magnetic field lines are getting closer together. It causes a direction of force on this particle, this charged particle that's moving, that slows it down and can even reflect it. And magnetic fields can form a magnetic mirror, or if the field is shaped on the left side to also pinch in, it can be a magnetic bottle. The Earth's magnetic field is a magnetic bottle. The field lines get closer together at the poles, both the north and the south. So charged particles that get trapped in the Earth's magnetic field bounce back and forth in a sense. They take these helix paths back and forth from North Pole region to South Pole region, and they get trapped in this region called the Van Allen belt, discovered in the late 1950s by Dr. Van Allen at the University of Iowa. And these are regions where there are more charged particles than in other regions of space, near the Earth or around the Earth, far from the Earth. So our International Space Station orbits inside this inner Van Allen belt, If an orbit was set up in this belt, that would be a high radiation danger and dangerous to humans over an extended period of time. But the Earth's magnetic field is somewhat of a shield for us from charged particles, high-energy charged particles coming from space. They guide those particles towards the poles and make the aurora. Our atmosphere is also a shield for us. So we'll be talking about magnetic field in this chapter. So that's, I think, about where we'll stop for our studies today. There's some more information in our textbook that you should read, our OpenStax Physics textbook. Be sure to do that and practice on some of the problems. We'll be putting some practice problems on YouTube also.